Okay, AP Physics, it's time to wrap up Chapter 30 and get ready to move on into Chapter 31. Last topic in Chapter 30, Gauss's law of magnetism. Recalling Gauss's law for electric fields, closed integral of E dot dA is equal to Q enclosed over epsilon naught. That E dot dA is electric flux, whether we write it in algebra form, phi equals E dot A, or in calculus form, integral of E dot dA. It only became a closed integral when we applied it to a Gaussian surface for Gauss's law. And you've got a picture there of an electric field from a positive charge and a surface. If we now consider, first of all, what magnetic flux is, magnetic flux, same concept as electric flux, just a different kind of field. So you're still dealing with the field lines penetrating the area, the concentration, the density of those field lines. Mathematically, magnetic flux, phi sub B, is equal to B dot A, which in calculus would be the integral of B dot dA. So you're looking at that magnetic field line intercepting a given area. So if I have, for example, a permanent magnet, and we ponder the field lines on that permanent magnet, always in the direction that a north pole would be attracted, then those field lines are going to go from north to south. Now, those field lines also, going all the way down to the level of the atom, continue inside. So that's the basic idea of magnetic flux. Now, let's apply it to the idea of Gauss's law. With Gauss's law for electric fields, we introduce the idea of a closed surface. So let's ponder a closed integral of B dot dA. Well, if we picture a closed surface, use your imagination. This is now a cube. So if I move this cube around to different locations, any lines that enter one side of the cube will also exit the other side of the cube. Anytime I have a closed surface, I will have as many field lines enter as exit the other side. That means when I integrate, when I sum all of the field lines, I'm going to have to get a zero. With an electric field, you had lines that, in this case, exited the surface, but you didn't have any field lines that were entering the surface. So you ended up with a net flux, which you got by the integration, and so then you got a value, Q enclosed over epsilon naught. With a magnetic field, you're always going to get equals 0, and that's because you cannot have a north pole without a south pole. In electric fields, you can have a positive charge without a negative charge, but there are no magnetic monopoles. And so really Gauss's law for magnetic flux is just that the closed integral, any closed surface, you always get a zero flux. The main concept here is the idea of a magnetic flux. Chapter 31, Faraday's law of induction. We're going to start with an investigation of a magnet and inducing a voltage in a wire coil. Ideally, we would do this hands-on with equipment, but can't do that these days. And so the next thing you're going to go to is an online simulation with a Google form that you're going to be walking through, making observations and drawing conclusions. Think about what you're doing and what is causing that voltage. Make notes, draw conclusions, and we will come back and ponder.